Okay, this is for Physics 5B Summer 2020. Um, it's August 11th, and so now we're on to chapter 24.1. And I didn't have anything in PowerPoint about 24.1. I started on 24.2, and the reason being there's like one little thing here in 24.1. I guess this equation we want to be able to understand that. That's the speed of light c, and then you've got the two. We've already looked into these. So you can see the numbers that they're equal to. And it turns out they don't show you why this is, but they've got Maxwell's equations here, and you need calculus to be able to really use these. But they have the general conceptual ideas behind them, so you can read through those. There's stuff we've already covered, like magnetic field lines are continuous. You've already had, I think, quiz questions and exam questions about this. No magnetic monopoles, in which you always have a north and a south. This is stuff conceptually we've covered, but you don't see anything about Maxwell's equations and the problems really. This is the only thing, and it's because you need calculus to be able to do anything with it. All right, so where I start is 24.2. So now we're talking about electromagnetic waves, and in general, a wave is a disturbance in a medium. So you throw a rock into the water, you get a water wave as a result. You talk, you produce a sound wave because you're making a disturbance in the air molecules, and also just all sorts of things. So if we make a disturbance in the electromagnetic spectrum or electromagnetic field, then we get a wave that moves out as basically one of the electromagnetic waves that we're going to talk about here shortly. So we talked about earlier about I think earlier we talked about what you vibrate an electron, and it's like vibrating the Earth. You got two satellites; they feel gravitational pull due to the Earth, depending on how far or how close they are to the Earth. And then you move the Earth but don't move the satellites. Suddenly the forces on the satellites change, and that information has to move out in the gravitational field towards those satellites, and it moves out there at the speed of light. And then the satellites say, "Oh wow, I've got a smaller force acting on me because the Earth moved further away." Or the other satellite might say, "Oh, I got a bigger force acting on me." Same thing, like take an electron and a proton. So if the electron's close to the proton feels a large electromagnetic force on it. You move the electron away, and then it's going to feel a smaller force. And so just moving that electron is going to cause a disturbance in the electromagnetic field, and all the other charged objects in that field that feel a force due to that electron are going to have to get the information to them that there's been a difference. So when we vibrate electrons, we produce an electromagnetic wave, because basically you have the charge of the electron itself, that's the electric field. Then you have the electron in motion, that's the magnetic field, and they kind of go together. So here's the picture. I don't know which one's which. See, okay, I guess the blue is the is the electric field, and the B is the magnetic field. So I guess the red is the magnetic field, the blue is the electric field. And so they go perpendicular to each other, okay? They go perpendicular to each other, and they move along this axis at the speed of c, the speed of light. So changing a current changes its charge distribution. Each charge has an electric field associated with it, and if it is in motion, a magnetic field associated with it. Changing the current changes the E field and the B field, the electric field and the magnetic field, and these disturbances move out in the electromagnetic field at the speed of light. These disturbances move out from the source like waves. It can be shown, and then here's what they have. This is the electric field divided by the magnetic field equals c, where c is the speed of light. So the ratio of the strength of the electric field to the strength of the magnetic field, that stays constant. That's just equal to c. So if one goes up, the other one must go up. If one goes down, the other one must go down. If E is 1 or whatever, whatever, the ratio has to stay the same. It has to be equal to 3 times 10 to the 8th meters per second. Okay, production of electromagnetic waves. The relationship between wave speed, wavelength, and frequency. This is what the book goes into now. So the speed of a wave is equal to the wavelength times the frequency. So c, if we're talking about one of these electromagnetic waves in a vacuum, is equal to the wavelength of the wave times its frequency. Okay, c is a constant in a vacuum or in air, 3.00 times 10 to the 8th meters per second. Therefore, we see that if the frequency increases, the wavelength must decrease. And if the frequency decreases, the wavelength must increase. The product of these two, these one times the other, that has to stay the same. So if one goes up, the other one must go down the same amount to keep this equal to 3 times 10 to the 8th meters per second. So here's the electromagnetic spectrum. This is the best one I've ever seen. It has tons and tons and tons of information. It's out of an astronomy book. But you can see here, it goes all the way from, I think I got the list down here someplace. It's going to go from radio, microwave, some electromagnetic spectrums you see we'll put microwave within the radio part of the spectrum. But anyway, radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays, okay? So, if we go back up here, the radio waves, they have the huge wavelengths, very, very long wavelengths, peak to peak, that's very big. We're talking the size of mountains, we're talking the size of buildings, we're talking the size of people, we're talking fingernails here, see we're still in radio, we got the microwave here. So look at microwaves, like the size of your fingernail, okay? So now what are we talking, a couple of centimeters? Then we get to a pinhead, and now we're kind of at the border between microwave and infrared. So here's infrared right here. And now we're talking dust particles, we've got the, I can't read that, what is that? Okay, so this is actually bacteria, virus, like the COVID-19 virus. That's what, they'd be the size of the ultraviolet waves. That's why, I mean, you're hearing that ultraviolet radiation could kill this. I've heard that some places. They take some things that are like packages and they just to make sure they put it under ultraviolet light. So the ultraviolet light's the same size as the virus itself. You had the visible right here. This is the part that we can see. It's very, very small. And again, the wavelengths are like the size of bacteria, a little bit less than the size of dust, a little bit about the size of bacteria. Then viruses, we're getting into the ultraviolet radiation. Then we get into the atom itself, and now you got X-rays. Okay, X-rays can do damage to atoms. That's why everybody always has to protect themselves when they're getting their X-rays done. And then you've got the gamma rays, the shortest wavelength of all. Look how short those wavelengths are. They're the size of the atomic nucleus. Matter of fact, at the point of a supernova, when a star blows up, core collapse supernova, one of the things that happens is that you get all these incredibly energetic gamma rays that can actually destroy an iron nucleus. The most stable nucleus there is, the strongest nucleus there is the nucleus of an iron atom. And these guys have so much energy, they can just destroy an iron nucleus. So we're talking really big energy. These are low energy, all the way up to high energy. The energy increases as we go across from radio waves to gamma rays. The wavelength increases, the wavelength decreases, the frequency increases. So it's energy and frequency increasing as we go from radio to gamma, but it's the wavelength that decreases, goes down as we go across the spectrum. And so you get an idea here of, this is the electromagnetic spectrum. This is the moving electrons causes a disturbance. These are the disturbances in the electromagnetic field that move out through space, including light that we can actually see. Okay, so, oops, I went too far. Okay, the electromagnetic spectrum. Let me try something real fast. Let me try it on this. I think the last time I tried to do this, I hit the wrong button and screwed everything up. Anyway, so again, this is the you've got this on your PowerPoint too, that if you downloaded it, and then basically here we can see it again. Okay, the same thing it's on above. On one end of the spectrum, radio waves have the longest wavelength. We can see that right here. The smallest frequencies, they got the low frequency, and the least amount of energy. Okay, they can get electrons in your antenna to vibrate up and down to make an electrical current that goes to your radio, and then your radio then puts it out onto a speaker and turns it into a sound wave, turns it from an electromagnetic wave into a sound wave. It travels from the radio station to your radio as an electromagnetic wave, so it travels at the speed of light. That's why everything's like instantaneous. It's not until it gets to your radio that your radio converts it back into a sound wave, where it's only traveling 340 meters per second. Okay, on the other end of the spectrum, gamma rays have the shortest wavelengths, the greatest frequencies, and the most amount of energy. Okay, we talked about that. The order of decreasing wavelength and increasing frequency and energy is radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. All waves travel at the speed of light c, 3 times 10 to the 8th meters per second in a vacuum, something like 2.999998 or something like that. And then in air, it's something like 2.9998 or something. They're both practically 3.00 times 10 to the 8th meters per second. Now, the part of the spectrum that we can actually see with our eyes is called the visible part of the spectrum. Okay, red, notice up here, red is next to infrared. See, this is the visible part right here. So the red here is like right here, all the way up to the violet over here, which is over here. So the red is right next to the infrared part, so it has the longer wavelength, the lower frequency, lower energy of the visible light. Then on the other end, we've got the violet light, and that's right next to ultraviolet. Okay, so the visible light, violet has the shortest wavelength, the highest frequency, and the most amount of energy. Okay, so the part of the electromagnetic spectrum that we can actually see with our eyes is called visible. Astronomers actually call the whole thing light, so that you might hear somebody go, oh yeah, you know, the light energy, and they're talking about X-rays. Wait, you're talking about X-rays, you're not talking about light. No, everything to them is light. Okay, visible part is the part that we can see. Okay, it sits right between infrared and ultraviolet. On this part of the spectrum, red light has the lowest wavelength, the longest wavelength. Oops, I read that wrong. I was going, wait, what did I write here? I read it wrong. I wrote it right, but I read it wrong. On this part of the spectrum, red light has the longest wavelength, the lowest frequency, and the lowest energy. Violet light has the shortest wavelength and the highest frequency and the highest energy. In order, it is red, orange, yellow, green, blue, indigo, and violet. So a mnemonic that helps us remember it is Roy G. Biv. Just remember some guy named Roy G. Biv. R is for red, O is for orange, Y is for yellow, G is for green, blue, B is for blue. Then they got indigo in there for Val, I guess, or maybe it is an important color. I'm not sure. It's one you don't hear about much. And then you got violet. All the, so most of those, all of those you hear about except for indigo. You hear about indigo when? I don't know when. Okay. So you got Roy G. Biv. So you got the longest wavelengths over here with the red, lowest frequency, lowest energy, all the way up to the high energy, high frequency, short wavelength, violet light. And it goes right in order as Roy G. Biv. Okay, this is a highly recommended video that you watch. I'm at Sac State, so when I upload this, even if this is an hour and a half long, it's only going to take, what, 45 minutes? It's not going to take the 12 hours or 16 hours, whatever it does to upload it from my home computer. And I don't have internet at home anyway right now. I don't know what happened. But anyway, this I would highly recommend watching this. This is a very good video. Maybe we can watch a little bit of it. Do I have to push something? I didn't think so. Okay, this is it. I remember now the reason I can't really play these videos on here, because the sound is horrible. The microphone is trying to pick up the speaker from this guy. So anyway, goes through and it tells you about the different types of electromagnetic waves you've got.
Electromagnetic waves, or EM waves, are similar to ocean waves in that both.
So it's really a good video. So anyway,
waves have crests
even if I decided we could have time to watch it, because I can upload so fast here at Sac State, I don't think you can hear the sound. I discovered that when I screwed up. Oh, okay. No student grades are on here. Whoa, I don't want to do this. Okay, but I screwed up, and some student grades got, where are we looking at? Some student grades got on there, and so I had to, we're here? Okay, so I had to I tried to rerun the whole thing over again, hitting pause right when we got to the part where the student grades from Sac City showed up, and then that looked like it went fine. Then I went back and listened to it, and the sound was just horrible, because what it is the mic from this guy trying to pick up from the speaker from this guy, and that's not the way to do it. Okay, so anyway, I would highly recommend watching, where'd it go? This video right here. Okay, it's a very, very good video. Okay, then, is this the end? Oh, this is the end. That's the end of it. Okay, so online number 8, chapter 24 problems are all here. Okay, so here's the first one. So it just says, verify that the correct value for the speed of light c is obtained when numerical values for the permittivity and permeability and permittivity, this is permeability, this is permittivity of free space, mu is 0, epsilon 0, are entered into the equation c equals 1 over the square root of mu 0, e 0, or epsilon 0, So then, yeah, you plug it in and you get 2.998 times 10 to the 8th meters per second, which is as good as, if you're going to have 3 digits, that would be 3.00 times 10 to the 8th. Okay, then another thing that we had, I showed you this. The electric field, well, actually we had C equals E over B, which means that E is going to be equal to CB. So it says the maximum magnetic field strength of an electric field is 5 times 10 to the minus 6 Teslas. It's even less than the Earth's magnetic field. Calculate the maximum electric field strength if the wave is traveling at a medium in which the speed of light is 0.75 c. So basically you have 0.75 times the speed of light, 3.00 times 10 to the 8th, times your magnetic field that they gave you right here, and you get 1.1 kilovolts per meter. Remember, that's the units for electric field. Volts per meter, kilovolts per meter. All right, so very simple. That was all that chapter 1 stuff. Okay, then you've got calculate the range of wavelengths for AM radio, given its frequency range is 540 to 1,600 kilohertz. Do the same for FM with the range of 88 to 108 megahertz. So all you got to do is use this equation here that we already saw, C equals frequency times wavelength. The wavelength is what we're trying to find, so that's C over F. C doesn't change, and we're given all the F's. So it's just a matter of going in and plugging and chugging. So you got 3 times 10 to the 8th divided by your 5.4 times 10 to the 5th hertz, which is the same as 540 kilohertz. And then you get that wavelength. Remember, the wavelengths for the radio waves are very, very long. Okay, that'd be 556 meters. So that is almost 6 football fields in length for those waves. So they got very big wavelengths. And you can see for the other end, you've got 1.88 times 10 to the second. Then when you do it for the FM, you get shorter wavelengths. Okay, but still 3.41 meters. That's like 3.5 meter sticks. You guys have all seen meter sticks. And then a little less than 3 meter sticks would be the other one. So that would be the range of wavelengths for FM. Okay, find the frequency range of visible light given that it encompasses wavelengths from 380 to 760 nanometers. Well, you just do the same thing. You got your speed of light, but now you're solving for frequency. Up here we solve for wavelength. Okay, down here we're solving for frequency. Okay, and so you got your frequencies it's just a plug-in thing. Okay, you wish to detect details of the size of atoms about 1 times 10 to the minus 10 meters with electromagnetic radiation. It must have a wavelength of about this size. What is the frequency? What type of electromagnetic radiation might this be? All right, so you get basically your wavelength needs to be this number here is what you're looking for. C is set. C is set. So you simply solve for frequency because that's what you want. You plug in your 3 times 10 to the 8th meters per second divided by your 1 times 10 to the minus 10 meters. You get 3 times 10 to the 18th hertz. So where would 3 times 10 to the 18th hertz be? We're on this one. Let's go back and look. Hey, how come this thing isn't moving? Oh, because I was already at the bottom. All right, so let me go current slide. Oh, that wasn't the current slide. Here we go. No, I forgot what it said. It's 10 to the 18th. So I can't remember. It was 10 to the 18th, something 10 to the 18th. Well, obviously that's X-ray. You also notice there's overlap. Some people. It depends on the discipline you're in. Different disciplines would call these wavelengths, these frequencies, soft X-rays. Other ones would call them far ultraviolet. I guess they haven't gotten an international committee together to have the exact boundaries. You can even see that hard X-rays they overlap with gamma rays. But 10 to the 18th looks like there's like 10 to the 19th, 10 to the 17th, 10 to the 18th looks like it definitely is an X-ray with nobody arguing that it's something else. Nobody arguing that it's ultraviolet. Nobody arguing that it's X-ray. Okay. You know you got X-ray right there. Oh, 3 times 10 to the 18th. Okay, and then now that's chapter 5. So here's chapter 5. So now we're talking about the aspect of light. And the book talks about rays, and so this is a picture I made for another class earlier this summer, I think for one of the Sac City classes, because I didn't like the way the book was doing it. But here's a light bulb, What you can imagine is kind of like spherical bubbles of light coming off of there. And they go out and they move out away from the light bulb. And they get out here, they start to look parallel. You get far enough away, and we're only talking about a few meters where this will work. They'll be practically parallel to each other. So the wave fronts basically are like the surfaces of the light as it moves out kind of radially, kind of like bubbles, big huge spheres getting bigger and bigger as it moves out away from the light bulb. Now what the rays are, those are drawn perpendicular to the wave fronts. So there's a ray, there's a ray. We draw them perpendicular to the wave fronts. Okay. Wave fronts of light, like bubbles, getting bigger and bigger, expand out from the light. Light rays extend perpendicular to the wave fronts. The rays show the direction the light is traveling in. Oh, now we're already up to section 25.2. The law of reflection. When light is reflected off a surface, we find that the angle between the incident ray and the perpendicular to the surface is equal to the angle between the reflected ray and that same perpendicular to the surface. In other words, here's the incident ray. This is where the light comes in, boom, it's right there. Then it goes off like this. This is the incident ray, this is the reflected ray. So it's bounced off the surface already. We draw a perpendicular to that surface, 90 degrees, right here, 90 degrees to the surface. Measure this angle with a protractor, for example. Measure this angle, again with a protractor. We'll find that this angle and this angle will be equal to each other. So the law of reflection states that the angle of reflection equals the angle of incidence. You don't use this angle. Okay, you may say, well, that'd be the same. Those would also be equal. Yeah, but here, let me do this. Okay, here's another figure in your book. See, the rule of reflection, law of reflection, the way that is, it always works. But if you look at this surface, if you try to go measure the angles this way, you're not going to get the right angles at all times. And on curved surfaces, where are you going to do your angle? So you always want to do the perpendicular to the surface and measure that angle. Then the rule of reflection will always apply. The one where you take the other, you try to measure it over here, that's only going to work for flat surfaces. If this surface isn't flat, it's not going to work for this surface, okay? All right, so theta I, theta incident angle equals theta R. Okay, and then you can see some examples. This is an example your book has. Our image in the mirror is behind the mirror. So in other words, if you didn't know you were looking at a mirror, you didn't know what you looked like, you might think you're looking at a window, and there's a person on the other side of the window the same distance you were in front of the window. So light comes from the foot, okay, so light goes up, strikes the mirror, bounces off the mirror, makes those two angles equal, goes up to your eye, but you might think the light came from over here. Okay, so this is actually a virtual image. Light never actually passed there. But you might think the light came from over here, okay? Because that's where it looks like the foot is. And then same thing, here you are, you're looking at the top of their, here's your top, the top of your head light goes like this. This is the incident, bounces off, this is reflected, goes to your eye, you look back, and then boom, there you are looking at the top of your head. But you might think that's somebody person if you don't know what you look like. Say, yes, look at that person up there. That little person looks kind of like me. What are they doing running around here looking like me? So if you thought you were looking at a window, you could be fooled, but you're actually looking at a mirror. Okay, now we're all the way up into the law of refraction. Okay, the changing, I'm going to take a break for a little bit. Hold on a second. Okay, here we are in chapter 25.3, the law of refraction. Okay, refraction, the changing of a light ray's direction, loosely called bending. The light is bending as it goes from one medium to another. When it passes through variations in matter, is called refraction. Okay, the variations in matter, I got that out of your textbook. So anyway, you've got something out here like air, for example, and you got something down here such as water. And the light travels in like this, gets to this point here, and then some of it is reflected. We're not worried about that right now. A lot of it is refracted. It's bent. See, the light was traveling in this direction, but now it's traveling in this direction. And that's a good thing because we can take advantage of that for all sorts of things like eyeglasses, telescopes, microscopes, all sorts of things that allow us to focus light, make something that's a long ways away seeable with a telescope, or something that's very, very small seeable with a microscope. Light travels at different speeds in different substances. So when we talk about light having a speed of 3 × 10⁸ meters per second, we're talking about air, we're talking about a vacuum. But in something like water, it actually slows down. See here, light has a speed of 3 times 10 to the 8th meters per second, but in water, its speed is only 2.25 times 10 to the 8th meters per second, so it slows down quite a bit. Okay, why does this happen? So imagine we're up in a hot air balloon and we're looking down on a marching band, and with a time-lapse exposure, I think what that means, to me what that means is, I looked it up to make sure I'm using this word right, and I'm still not completely sure one way or the other, but it's like you take a picture every 1 second, and on the same photographic plate. So you get, here's the band when you first take the picture, here's the band a second later, they're on the parade ground, so they're marching pretty fast on the parade ground. Then they get to the plowed field. They're going to slow down on the plowed field. So this guy comes in, this guy's going to slow down first. Then this guy's going to hit it, and that guy's going to slow down, and so on and so on. So now, if you notice that there's a bigger difference between them here than there is here. So they're not moving quite as far per second as they were when they were on the parade ground and as they are in the plowed field. Now when they get out here, now this guy's going to get out to the parade ground and start moving faster. I wish they had more details in between here on this picture. I got it off the internet. But you can see that this guy's going to start moving faster. Now they should be moving faster. Okay, there's a little bit greater distance between them. All right, so this is like the wavefront that we talked about earlier. Wavefront, wavefront. This is the ray, the direction that the band is traveling in, okay? So from a hot air balloon, we look down on a marching band, and with a time-lapse exposure, taking a picture every 1 second. The band can march much faster on the parade ground than they can on the plowed field. As a result, if the band meets the boundary at an angle, the direction of their march changes. If they came straight on, perpendicular to it, I mean, they came right along this line here, the ray was perpendicular, they would just slow down. There wouldn't be any bending. So they got to come in at an angle in order for there to be bending. Okay. So here's more of what I'm trying to show. So this could be like air and glass, for example. So this would be the wavefront, wavefront, wavefront. Now when the wavefront gets to this boundary, this part of the wavefront that has already entered into the glass is slowed down. Then this part here, this part's still out here fast, but the rest of it is slowed down. It's entered it. Now it's all within the glass and it's all slowed down. I try to make it so like this is a bigger distance, like every, I don't know, microsecond or something like that. We took a picture, and then here they don't travel as far. So this is what happens. It goes this way, and then it goes this way. Now you can imagine if you're going the other way, you're going to bend this way. You're going to bend the opposite direction because these parts get out into the air first. Okay, light moves faster in air than it does in glass and everything else except a vacuum. So so light travels faster than anything else we run into in our everyday existence. Sprite, 7-Up, olive oil, everything else. Light's going to travel faster in air than it does in those substances. Glass, whatever you want, cellophane. As light reaches the boundary between the air and the glass, such as a lens, it slows down. If it impacts the boundary at an angle, it also bends. And then you can see the light coming in, bending, and going like this. Okay, the index of refraction of a substance is the ratio of the speed of light in a vacuum, that's the 3 times 10 to the 8th meters per second, divided by the speed of the light has in that substance. It is a value that has been measured for many different substances through extensive lab work. So we have the index of refraction for a whole ton of stuff. Let us find the index of refraction for water. So speed of light, so index of refraction N, C over VW, the velocity of light in water. See, it's the index of refraction. It's a ratio of the speed of light, C, divided by the speed light has in that substance. Okay, so there it is right there. So you got the speed of light in air, in a vacuum in air, same thing basically. Then you've got what the speed was in water. I told you that up here someplace, up above someplace. Okay, so it's going to be 1.33. The index of refraction is unitless and is always equal to or greater, is equal to 1 or greater than 1. Okay, why is that? Well, it's always C on top. And if you came up with some number that was going to be for an index of refraction that was less than 1, that means this number down here has got to be bigger than the speed of light. The light travels faster in this substance than it does in a vacuum, which doesn't happen. We've never run into that. You could find some substance that makes light travel faster than the 3 times 10 to the 8th meters per second, you would be winning Nobel Prizes for the rest of your life. So people, that doesn't, as far as we know, it doesn't exist. But who knows? 1,000 years from now, who knows what they'll find out? If we were in this class 100 years ago, I'd probably be telling you stuff that was scientific knowledge then, but now we know, whoops, that wasn't quite right. Okay, and then I just have a bunch of index refractions for a bunch of different things right out of your book. I just took these right out of your book. So you can see air, the index refraction is like 1.00033293. Okay, so it's very, very close to 1. So in other words, if you're going to find, in other words, another way to look at this is that um, the velocity in the substance would be equal to c over n. So just put the velocity up here, put n down there. So you'd have the velocity in air, for example, equal to c, 3 times 10 to the 8th meters per second, times almost exactly 3 times 10 to the 8th meters per second. So you'd get this number here, which is almost 1. You'd have to go out, like after the decimal place, you have to go out 4 places just to find something that's not a 0 there after the 1. Carbon dioxide, very close. This is all gases. So the gases, that's why we say in the atmosphere, and these are all make up the air in the atmosphere in general. We don't, there's not very much bending going on. Now in liquids, it's a different story. You got benzene, which is 1.501. You've got carbon disulfide and so on. You got water down here, fresh water. So that's the 1.333 that we calculated someplace, right? Right there, 1.33. And then in solids, you got diamond, 2.419. I think that's what causes diamonds to sparkle or do something that gets people all excited. They got that high index of refraction, very high. And then we got glass, crown, glass flint. You got ice at 20 degrees Celsius. It's like 1.31, just about, and zircon and so on. And then, let's see. Oops, we skipped a bunch. Okay, Snell's law. Dang it. Okay, Snell's law. So you got 2 substances. You could have air up here, you could have water down here, for example. Okay? So we've got the index refraction for one substance times the sine of theta. That's the angle that the light makes with the perpendicular. Okay? So here we're talking about the index refraction of this out here, whatever it is. It could be air, it could be glass, it could be anything. Then you've got the angle that the light coming in makes with the perpendicular, the sine of that angle, equals the index refraction of the other substance, whatever this is, times the sine of this angle down here, the angle that it gets bent at. Okay? So there's Snell's law. Suppose a ray of light from air to water making an incident angle of 30 degrees with the perpendicular to the substance. So suppose a ray of light travels from air to water making an incident angle of 30 degrees with the perpendicular to the substance, like, to the surface. I guess that's okay. What would be the refracted angle? So you got the index refraction of air, which is just 1, sine theta air, which we were told was 30 degrees, equals index refraction of water, which we know is 1.33, sine of the angle for water. Okay, so you solve for the sine of angle. So you bring this over here, so you got that on the bottom, and you take the arc sine. Okay, so then you've got this, you plug in your numbers, you got your 1 for your index refraction for air, you got your 1.33 for the index refraction of water, you got your 30 degrees because that's this angle here, and you get 22 degrees. So this angle down here would be 22 degrees. So we're bent towards the perpendicular. We're bent towards the perpendicular. This was 30 degrees coming in, but now we go out at 22 degrees to the perpendicular. So we got bent towards the perpendicular. Now, what if light was traveling from water to air? Well, we just reverse things. We solve for the air, arc sine, the index refraction for water, times sine theta water, okay? So basically now we do the same thing, except our index refractions are reversed. We got the 1.33 on top and the 1 on the bottom, okay? We get 42 degrees. That means you're bent away from the perpendicular. So you can think of it maybe going this way. Say the light wasn't going this way, but was going this way. Boom, it would do that. Okay? It would go the opposite direction actually. So okay, so it would get a larger angle. Okay, from the examples above, we see that light travels from a medium it moves faster in. Okay, from the examples above, we see that when, I left out the word when, light travels from a medium it moves faster in to a medium it moves slower in, its path of travel is bent towards the perpendicular, okay? So from air to water, it's going to be bent towards the perpendicular. From air to glass, it's going to be bent towards the perpendicular. And if light travels from a medium that moves slower in, such as water into air or glass into air, to a medium it moves faster in, its path of travel is bent away from the perpendicular. Oh, this is it. Okay. All right, so I told you there wasn't much on these guys. Okay, so here we are. We're ready to do these guys. Okay, so this is chapter 25, number 6, your own. Okay, what is the speed of light in air in crown glass? Well, we have this equation here. Okay, so you just go back, you look up the index refraction in air. It's like 1.00293. Remember, we had that. Air, 1.000293, so we're using that now. Okay, 1.00293 divided in, and they got all these, see, you can see it's basically 3.00, but this is actually what it is out to all these decimal places. And so you get 2.9964. So that would be the speed of light in air. So that's why we can call it 3.00. As long as we don't go out too many decimal places and your book likes to use 3 digits, we can call it 3.00 times 10 to the 8th meters per second in air. Okay. Now in crown glass, well, we go back to our go down 2, I think. Yeah, liquids. Crown glass, you got the 1.52. 1.52. So you've got your speed of light, and we go back to just the 3 digits of accuracy here, because you only have 3 digits of accuracy on this guy anyway. So you get 1.97 times 10 to the 8th. So it's slowed down quite a bit from 3 times 10 to the 8th. So we're going a lot slower. Okay, this is number 7 in your own. Calculate the index refraction for a medium in which the speed of light is 2.012 times 10 to the 8th meters per second, and identify the most likely substance based on table 25.1. So there's the velocity that they're telling us that this thing moves at. There's out to so many digits is the speed of light. So we get 1.490, 1.490, 1.49. Okay, I think these guys are, we can rule 1. Well, we can't rule these guys out. Glycerin. We can rule these guys out. So liquids 1.49, and none of those are that close. And then 1.49, 1.4 is 1.43, but 1.4 there. It looks like this one. I don't see anything else that's closer than that. So most than likely it's the polystyrene. And if we go back and take a look, polystyrene. Made up problem. Yaron, I gave you the one problem that Yaron has. I mean, Yaron himself, I know Yaron. He did not write these questions. Someone else wrote the questions, probably a grad student someplace at some university. And they should have had more problems like this. Instead, they have these really out there problems that aren't helping people understand, who are seeing this stuff for the first time, understand the basic of what's going on here. Okay, some of them are just downright ridiculous. So I had to make this one up. I gave you the one. Number 10 is just like the ones that I just did. Number 10 is like these guys. Why isn't this thing moving? There it goes. So number 10 is like these. These are the kind of problems I'm talking about, what we just did here. So number 10 is like the only one in your book that is like this. The others are, I don't know what they're trying to accomplish with the other ones. Again, it wasn't your own, someone else wrote the problems. I don't know if he had final say in what went into the book or not, though. All right, so if light travels from air to crown glass, okay, we already looked that up, that's 1.52 index of refraction. The angle of incidence is 42 degrees. What is the angle of refraction? Well, we set it up, there's air, it's going from air to crown glass, so there's NA, sine theta A, then I have CG for crown glass, okay? So we solve for crown glass angle. We got arc sine, this guy over here, divided by the index of refraction for crown glass. Plug your numbers in, plug in the 1 for the air, so it's like you can maybe even start ignoring it even. Divided by 1.52, so 26 degrees would be the answer. And that's it. Okay, so we are complete. I'm going to try to put something together for you guys to use PHET because I feel so rotten that I didn't get on top of that. Um, but it'll be like really easy. I'll make a video. That's why I'm bringing it up. I'll make a video showing you how to do these little things. You can follow along in the video. That I may just keep one little last thing that you might have to do, but based on what we've already done, it should be like incredibly easy just to do that. Then when I go look at them, I'll say, okay, that person did do that. So that's the way that's going to work. So I'm going to work on that. Let's see, it's 11:24, so we've got our Zoom meeting coming up. So I better not upload this yet, or maybe I can try. Wonder if I bet you we can run the Zoom meeting while this is uploading. All right, so I'll do that. So maybe by the time the Zoom meeting starts, this will be already uploaded. All right, so I'll talk to you guys at the Zoom meeting coming up in a little bit. If you're like, I already got people emailing me asking me if it's mandatory. I'm saying no, it's not mandatory. Um, might help, but it's not mandatory. And so we'll see who shows up to the Zoom meeting. And I think that's everything. And I'll see. I think that's everything. All right, I'm gonna start uploading this now. So I'll talk to you later.